guys, welcome to my YouTube channel. I'm Marta and I'm following the 4 steps to become an expert in robotics. The first step I have already completed. It was where I came out with this article called Atlas and the Secrets Behind the Most Dynamic Humanoid in the World. Please check it out if you haven't. Today's video is about the second step, where I built this self-balancing robot that you have just watched. I would like to properly introduce you to MOBO, which is a self-balancing robot, as I mentioned, because it only has 2 wheels, but always keeps itself balanced. Now you might be wondering, how does MOBO hold itself standing? Well, I'm gonna break it to you so you can understand all the behind the scenes, because it's actually pretty simple. Let's talk about physics. A self-balancing robot is much like an inverted pendulum, but you can imagine balancing a stick on your finger. Well, thankfully the robot is not as bad as I am, but this example was actually to show you that we move our finger in the direction in which the stick is falling. And the robot works the same way, only that it will only fall either forward or backward. So basically, whenever the robot falls forward, it will move forward, and whenever it falls backwards, it will move backwards. What we are trying to do here is to keep the center of gravity right above its pivot point. This is called inverse kinematics, because the robot will do the opposite of its tendency. To make balance easily achievable, it's important that the chassis has the flattest shape as possible, and at the same time that has a perfect weight distribution. The flat shape won't tend to fall as much, and the perfect weight distribution will prevent from any fall tendency, and at the same time will create enough inertia for it to move. The robot's actuators are the motors and the wheels. MOBOs are plastic gearbox ones, which are simple DC motors with a gearbox reduction so they can move more precisely. This is super important so they can have a better response to the inclination. To drive these motors, I used an L298N DC motor driver to control their spinning direction and their speed. This speed control is actually done by the PWM inputs from the motor driver. PWM values range from 0 volts to 5 volts that translate the quadratic waves input on the driver. But how does the robot sense its tilt? For us, it's easy to feel our body's balance, but for a robot to do so, it's essential that it has a sensor called MPU6050. This is a digital accelerometer and gyroscope, each with 3 axes, X, Y, and Z. This model is basically sensitive to acceleration, velocity, orientation, displacement, and any other motion-related parameters. This is what will tell the robot how much it has tilted and the speed in which it's falling. Basically, the robot is falling. The MPU sensor tells the robot how fast it is falling and in which direction, and then it goes back to place. Now, the magic trick behind it all comes up. So, as I told you, the MPU6050 gives certain information to the robot. But the way this robot processes that information is by using a controller called PID. PID stands for Proportional Integral Derivative. These letters actually represent values named Kp, Ki, and Kd, which are constants that calculate the error. Why is this? Well, in a perfect world, it would be enough for us to tell the robot that if it has tilted, it has to go back to place. But that is never the case. Here's where the error comes in. To allow the robot to balance perfectly, we use Kp, Ki, and Kd in mathematical equations to minimize the error and maximize the balance. To sum up, the better PID values, the better stability. That's it, guys. I hope you enjoyed the video. If you want to build the robot yourself, I left a link down below so you can get access to a tutorial. I also left my link tree so you can follow me on other socials, and please like and share.